We are going to start talking about motion now. We've been talking about the chapter 1 stuff previous to this. This motion stuff is the beginning of chapter 2. And we can look in the slides. We are now on O for motion. That's where we are. Motion along a line. The first slide of this is the reading assignment. It is literally everything, as I say down here. I want you to read this whole chapter and look at every single one of the examples in it. Try to work out the examples yourself for this entire chapter. Usually, we will be looking at an entire chapter or nearly an entire chapter going through this. We're going to be doing approximately the first 14 chapters. We'll skip a few, but for this chapter, we need to look at everything. This is all going to be about velocity and speed and direction and all that kind of stuff. Velocity is a vector, direction matters, speed is a scalar, direction does not matter. If you are driving in your car, you see a little thing at the on your dash called a speedometer, speedometer. That measures your speed, as you might imagine. If you also have your GPS or a compass, let's say you have a compass with you, then you have a compass and your speedometer. You can figure out your velocity from that. If you're driving south on I-95 going to Miami, I don't know why I keep using that as an example, but let's just keep going with it. Your speedometer says, yeah, you're going at 75 miles per hour. And your compass says you're going south. Those two together will get you your velocity, 75 miles per hour south. We have things called average velocity and instantaneous velocity here. Your average velocity is just going to be your total change in x over the total time that it took you to do that. If you drive down to Miami and it takes you 3 hours to get to Miami, what did I say, 300 kilometers down to Miami, then you'd be going 100 kilometers per hour. If you drove to Miami and then drove right back up here, then that would take you 6 hours, and your delta x would be 0. Your average velocity would actually be 0. If you drove to Miami and straight back, or drove to Miami and spent a day there and then drove back, your average velocity would be 0 because your delta x would be 0. Obviously, your speed, your average speed would not be 0, but the way that we define average velocity is just your change in position over the amount of time that it took. So that's an interesting, almost vocabulary thing, definitional thing when we're talking about velocity. If we look at the instantaneous velocity, that is the velocity at a particular moment in time. So, if I left at noon, then at this particular moment in time, 2:45 and 35 seconds, at that particular time, what is my velocity? That is the instantaneous velocity. And you can use that by finding the derivative of your position with your time. Direction obviously matters for both. And as I said before, we define right, east, north, and forward and up to be positive, left, west, south, backwards, and down we define to be negative. That's just because of the Cartesian coordinate plane that we define it that way. There's nothing really special about any of those directions. It's just for the sake of convenience, we define it that way. Here's some graphs that we can look at. The first two are looking at average velocities. You see the delta x and the delta t. Well, average velocity is delta x divided by delta t. And most of you have experience looking at this kind of thing in your math classes. You find the slopes between 2 points by finding the delta x and dividing it by the delta t. In this case, though, it's kind of backwards, because look at this. What we usually define to be our y-axis is actually our x-axis. This vertical axis that we have, we're calling x. And our horizontal axis, we're calling t. So always be aware of what the axes are actually labeled as. X-axis is actually going up, and y-axis, t-axis is going to the side. Just be mindful of that as we look at these. If we look at this last one, we see that the velocity is the instantaneous x velocity is the slope of this tangent line. We've got this green tangent line. We're looking at time equals 1. Look there at time equals 1 at P1. If you just draw a tangent line at P1, then that right there is going to give you your instantaneous x velocity. The slope of that line is your velocity. The slope of the x graph, if you're graphing x versus t, then the slope of that is the derivative of that, and the derivative of something, the derivative of x, the derivative of position, is velocity. The derivative measures the rate that something is changing. This is why it's important that you've taken Calculus 1 before this. The derivative of something is how quickly it's changing. If my position is changing very quickly, that means that I have a large velocity. If my position is moving one way or the other very, very fast, then that means my position is changing quickly. That means that I have a large velocity. If you have a small velocity, your position does not change very quickly. You look at a snail on the ground outside, its position does not change very quickly. You know, you come back 30 minutes later and it's made it halfway across your porch or whatever. And that's because its velocity is very low. So the rate of change of your position is your velocity. This, there's an organization called, well, they output a product called Physics Education Tools. And I believe that's their name. And they have all these nice applets that you can play with. Unfortunately, this one doesn't work anymore. And so I kind of had to make my own. So let's go to my own version of this, which is here. I have, I'm going to type in 0 there. I made this table. This, maybe it shouldn't be called acceleration table. It should just be called table of position, velocity, and acceleration. There's a lot going on here, as you can see. But I can take these initial things. These, at time 1, these are all the initial values. The initial value at time equals, actually I'm going to make it time equals 0 to just make it initial is 0. The initial position is 0, the initial velocity is 0, the initial acceleration is 0. If I make the initial position 12, let's say, so this means, visualize this in your head. You start on the x-axis. Let's just keep everything in the x-axis. And you start at a position 12. 12 meters to the east, let's say, of some position. If you want to think about this in terms of something you can visualize, visualize an intersection, some roads that are intersecting, maybe University Boulevard and Babcock Street. And let's say that you start 12 meters east of that intersection on the sidewalk. And you have no velocity and no acceleration. Well, if you have no velocity and no acceleration, then your position is going to remain constant. You're not going to move. You're always going to stay at 12 meters east of that intersection. Well, what if I give you a velocity of 2 meters per second, but an acceleration of 0? Well, if you're moving at 2 meters per second, then you'd start at 12, and then you'd move to, in the next second, this is the time in seconds, you'd move to a position 14 meters east of the intersection. 1 second later, you'd be 16 meters east of the intersection, then 18 meters east of the intersection with this velocity of 2. If you had a velocity of -2, then you'd start at 12 meters east of the intersection, and then you'd go to 10 meters east of the intersection. The negative means that you're moving west, as we've discussed. With a negative velocity, you'd move west. Now, how did I set up this equation stuff? Your position starts off as 12. You can see how I'm marking the positions like that. I hope you can see it in the video. Position 12 there. Here, for this part of the Excel spreadsheet, that cell is whatever, if I highlight it, it's B5 plus C6. This is B5, so it's whatever your position was last second plus whatever your velocity is. So every second, you're going to change position by an amount equal to your velocity. Every second, you'll do that. And so 1 second later, you're at a position 10. You've moved 2 meters to the west. You can keep doing that until you get to the intersection. Here, at 6 seconds, you're at the intersection. We're defining the intersection to be 0. And then you are moving onto campus. Campus is west of that intersection, so you're getting deeper and deeper into campus as you go on with that velocity like that. Now, what about acceleration? I'm going to set that to 0 and that to 0 so it's a little bit easier to see. Your acceleration is how much your velocity is changing. Remember here, your position is how much is, your velocity, excuse me. Your velocity is how much your position is changing. If I have a velocity of 3, then every second my position changes by 3. My acceleration, I'm going to make my acceleration 1.6, just to have something. If my acceleration is 1.6, then every second my velocity changes by 1.6 meters per second. And that means that my position is going to be changing, but it's going to be changing a different amount every second. If I have an acceleration, then my velocity is always changing. Acceleration means the rate of change of velocity. You can also think about it as if my velocity is changing, and here it is, my velocity goes from 0 to 1.6 to 3.2, my velocity is always changing. Well, if my velocity is always changing, that means that I must have an acceleration. This is the difference between position, velocity, and acceleration. This right here is one of the most important things to understand from this semester. The difference between position and velocity and acceleration. Acceleration is how quickly my velocity is changing. My velocity is how quickly my position is changing. I can start doing odd things as well. Let's say that my velocity starts off as 15 and my acceleration is -3, let's say. I can be going east, excuse me. Positive velocities are east. I can be traveling east at 15 meters per second, or 12 meters per second, or 9 meters per second, or 6 or 3, traveling east. But if I'm slowing down, looking at this, it sure does look like I'm slowing down. I start off going fast, and I slow down, and I slow down, and I slow down. That means that I have a negative acceleration. If I'm going in a positive, if I have a positive velocity, I'm going in a positive direction, but I'm slowing down from 15 to 3 to 0 to -8. Well, actually, let's ignore all that for now. I'm just slowing down from 15 to 9 to 0, whatever. That means that I have a negative acceleration. I could do the opposite, and I could have a negative velocity and a negative acceleration. That means, well, let's just look at this. I have a negative velocity. That means that I'm going west at 15 meters per second. But the next second, I'm going west at 18 meters per second. And then I'm going west at 21 meters per second. That means that you're speeding up, going west. You start off at a medium speed, and you go at a faster and faster speed west. That means that you're accelerating. And you can also have positive numbers like that. You start off going east. and with a positive acceleration. That means you're getting faster and faster in the east direction. You can even mix and match these. You can have -15 and +3. If it's -15, that means that I'm going west at 15 meters per second. But with a positive acceleration of 3, that means the next second I'm going to be going at -12 meters per second, and then -9, and the -6, the -3, and then I will stop. Whenever you get to 0, that means, oh, I've stopped moving. But if I still have the same acceleration, then I'm going to start moving the opposite direction. Imagine this in your mind. I'm going 15 meters per second west. Just imagine driving on an east-west road like University Boulevard. If you start at the intersection between University and Babcock, then that would be driving into the university at 15 meters per second west, but I'm slowing down. Now I'm going 12. Now I'm going at 9. Now I'm going at 6. Now I'm going at 3. Then I stop. And then I start going the opposite direction, like that. So for many people, it's easier to think about when it's like this. Now I'm going east on University. Still going east, but at a slower rate. Still going east at a slower rate, slower, slower. I stop and I turn around. You can have a positive acceleration, sorry, a positive velocity and a negative acceleration. That is totally okay. That just means that you're slowing down. You can have a negative velocity and a positive acceleration. That means that you're just going the opposite, you're slowing down in the opposite direction. You can have positive and positive. That's totally okay. That just means you're speeding up. You can have negative and negative. That's totally fine. That just means that you're getting faster and faster in the opposite direction. All of those are completely fine. If you are going well, I think those are good examples. I told you that the derivative of position is the velocity. Likewise, the derivative of velocity is acceleration. The velocity is the rate of change of the position. If my velocity is large, then the rate of change of my position is going to be large. I'm going to be changing position quickly. If my acceleration is large, then that means that the rate of change of my velocity is large. I'm going to be changing my speed very quickly, which you think of as accelerating or decelerating. You might be slowing down to go to a stop sign, for example. However, there's other derivatives. There's something called jerk, which is the rate of change of acceleration. If you change your acceleration very quickly, then that's called a jerk. Say you're sitting at a stop sign, stoplight. Say you're sitting at a stoplight and the light turns green. Well, you need to go from 0 acceleration to some acceleration. To change from 0 acceleration to some acceleration, you need to have what's called jerk. Just like if you went from 0 velocity to some velocity, you need to have an acceleration. To go from 0 acceleration to some acceleration, you need to have jerk. So the derivative of acceleration is jerk. The derivative of jerk is jounce. I'm not kidding. The derivative of jounce is snap, the derivative of snap is crackle, and the derivative of crackle is pop. Now, a lot of you have heard about the expanding universe. The universe is expanding. And a lot of you have heard that the universe is accelerating in its expansion. The universe has an accelerating expansion. Well, it turns out that the acceleration of the universe itself is changing. The universe does not have a constant acceleration. That means that the universe has a jerk to it. I know a scientist who helped discover that. We worked, I would say we worked together. I was the junior-most person on that project, and he was the senior-most person on that project. So take it for what you will. I technically worked with him. But he discovered that the universe had a changing acceleration or a jerk. Now, the newspaper interviewed him, and he talked about jerk like that. Just like I was talking about jerk, he talked about jerk. So the journalists decided to include that in the paper that they wrote up about him, in the article that they wrote about him. So the article that they wrote about him had a giant picture of him And the headline was, "Astronomers Discover Cosmic Jerk," with a giant picture of him. Obviously, it made it look like he was a cosmic jerk, but he had a good sense of humor, so he actually framed that article and put it up in his office because it made it look like the newspaper was calling him a cosmic jerk. I thought that was a fun story. He's a good guy. I will see you tomorrow. Have a great rest of your day.